Hello, Math 141, talking about slant or oblique asymptote. If the degree of the numerator is 1 higher than the degree of the denominator of a rational function, we have slant asymptote. Suppose if I have, say, f of x equals x cubed minus 2x plus 1 over x minus 5. Now, this rational function does not have oblique or slant asymptote because the numerator is 2 degrees higher. If I have f of x equal, let's say, x to the fourth minus 5 over, say, x cubed plus x plus 2, now I do have slant asymptote because the degree of the numerator is 1 higher than of the degree of the denominator. Let me go to the next page. Suppose I have f of x equals x to the second plus 5x plus 4 over x minus 3. Yes, I do have an oblique asymptote. How do I find that? Well, I'm going to use long division. I'm going to say x to the second plus 5x plus 4 divided by x minus 3. Okay. Doing the long division, let me fix my degree here. So first I'm going to put, first of all, every time the degree of the top is higher by 1, and when I do the division, my final answer will be something linear. I hope that part is not that part is obvious for you. So let's look at this one. If I put x in here, x times x gives me x to the second, then minus 3x. And if I subtract this from, I will get, let's see, that gives me nothing. I get 8x plus 4. And so now I'm going to put here x plus 8. And 8 times x is 8x minus 24. And if I subtract this, I get nothing here. That gives me a positive 24, and a 4 is 28. Okay. So let me change color to green. Let me give myself a little bit room here. So after we did this division, we got x plus 8, and this remainder here is going to be plus 28 over x minus 3. Okay. And so what's the equation of my slant asymptote? The equation of the slant asymptote is y equals x plus 8. Okay. And this part, not the remainder. Why not the remainder? Why don't we don't care about the remainder? And simply because as x is getting larger and larger and larger, like billion, 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 really, really big number, all this is going to 0. So the remainder does not concern us when it comes to slant asymptotes. Okay, let's try another example. Let me go to a new page. Suppose I have x cubed, let's say some g of x equals x cubed, say plus 4 over 2x to the second plus x minus 1. Okay. Do I have slant asymptote? I do. The degree of top is higher by 1. So how do I find that? Using long division. So I'm going to write 2x to the second. No, give myself a little bit room. How about starting here? X cubed plus 0x to the second plus 0x plus 4 divided by 2x squared plus x minus 1. Yeah. So what do I need here? What number times uh, 2 gives me 1? That's 1/2 and x. Okay. So 1/2 x times, let me not mix this with my 1/2 x times 2x squared gives me x cubed. 1/2 x times x gives you 1/2 x to the second. And 1/2 x times -1 gives me -1/2 x. So if I subtract this now, this gives me nothing. Then I have -1/2 x to the second plus 1/2 x. And I'm going to bring this 4 down, plus 4. Now what do I need? Now I'm going to put -1/4 in here, -1/4. -1/4 times 2x to the second gives me -1/2 x to the second, -1/2 x to the second. Then I have -1/4 x, -1/4 x, and then I have +1/4 plus 1/4. Okay, so I'm going to go ahead and subtract this. That gives me nothing. This gives me positive 1/4, and 1/2 gives me 3/4 x, and that gives me -1/4, -1/4 plus 4. So that's 3 3/4, or plus 15/4, plus 15/4. And notice that now this is my remainder. This is my remainder that we don't care for. Okay. So now let me just give myself a little bit room in here. I could manage in here. So y equals 1/2 x minus 1/4 is the equation of my slant asymptote. The equation of my slant asymptote. And once again, why don't we care about um, the remainder? It's because, as let me rewrite this in here again, because this is important to me. I really want you to see this. Let me give myself just a little bit room up here. So after the division, after using long division, g of x equals 1/2 x minus 1/4, and then the remainder, which was plus 3/4 of x plus 15/4, all over 2x to the second plus x minus 1. And notice that as for the very, very, very large values of x, the remainder approaches 0, so we don't care for that when it comes to slant asymptotes. Okay. Well, let's see. Let's do one last one. Suppose if I have p of x equals x cubed plus x to the second all over x to the second minus 4. Do I have slant asymptote? I sure do. Um, the degree of top is higher by 1, so let's use um, long division. I have x cubed plus x to the second plus 0x plus 0 using the dummy variables. And I'm going to divide that by, um, put a line around this so they don't get mixed. Divide that by x squared minus 4. Okay, so the first thing I need is x up here. X times x to the second is x cubed minus 4x, writing it under x's. And now if I subtract, okay, it's going to give me this just goes cancels this, so there's nothing. Bring the x to the second down. Negative times negative is positive, plus 4x. Okay, and now I'm going to go ahead and put plus 1. 1 times x to the second is x to the second, and 1 times negative 4 is minus 4. Subtract this. So I have now, uh, that gives me a 0. Bring the 4x down. 4x plus 4. And 4x plus 4 is my remainder. How do I know that? The degree of 4x plus 4 is now lower than this degree, so that must be my remainder. Okay, so let me give myself a little bit of room by erasing this part of my. So after doing the long division, we notice that p of x equals x plus 1 and the remainder plus 4x plus 4 all over x to the second minus 4. Once again, this remainder for the very huge values of x, approaches 0. So we don't care about this. So y equals x plus 1 is the equation of the oblique or slant asymptote. Well, I hope this was helpful. Thanks.